Now we're gonna start again with daylighting to actually understand deeply about the daylight, and then we talk about view and thermal comfort. All things you should know is that actually direct sunlight, ASE, schedule radiance parameters, radiance modifier, construction library, BASCA, UDI, view, GASG, and thermal comfort. And then in this workshop, you will get familiar with Ladybug Tools and its features. Ladybug Tools has 4 plugins, which are Ladybug, Honeybee, Dragonfly, and Butterfly. And it is validated by using some simulation engines such as Radiance, Plus, Open Studio, and actually also it is open source and it supports the community to engage in online forums. It is the 3rd most downloaded plugin. It also allows data transfer between the simulation engines. It is composed of modular components and it enables the exploration of design spaces. Moreover, it produces interactive 3D graphics and it's written in Python, and you can customize the algorithms based on your desired requirements. You can see actually you saw the capabilities and features in Ladybug Tools the last day. Also about the honeybee, about the dragonfly, and about the butterfly. And as you see in the picture, honeybee is integrated with butterfly and also with dragonfly and works with Radiance, Open Studio, and Plus. And the picture you can see. And then who is using Ladybug Tools? Actually, this tool is used by architects, engineers, consultants, and simulation experts from all around the world. So it is validated, and you saw the components and tabs for Ladybug Tools and the honeybees, and that the most using components that we actually which is are familiar with working on the canvas of Grasshopper. And there is a question: why do we choose LBT rather than a legacy? And the answer, according to the conversation in the Ladybug Tools forum, is that it supports many new features, quicker computation, and better practices. And now we want to understand deeply about daylight matrix definitions. So it's fine to read this invaluable paper. It provides all definition and it is a wonderful source to cite it. Now it's time to find out about the solar radiance, solar radiations and solar irradiance, which the difference between them is the unit. Solar radiation, called the solar resource of just sunlight, is a term for the electromagnetic radiation emitted by the sun. And solar irradiance is the power per unit area. And actually, solar irradiance is measured in watt per square meter in SI units. And as you see in the picture, it is clear that luminance describes the amount of light that is emitted from, and passes through and reflected of an object, we say candle. And it is measured using candle law per square meter, which is the concentration of luminance intensity per unit area. And there is a luminous flux. Actually, it is a measure of the perceived power of light, including infrared and ultraviolet and visible light. And the unit of luminous flux is the lumen. And the luminous intensity is a measure of how bright the beam in a particular direction is. The luminous flux includes infrared, ultraviolet, and visible light. We work on this region, visible light, and relates to daylighting analysis. The range of it is from 380 to 700 nanometers. And the visible light spectrum is the segment of the electromagnetic spectrum that the eye can view. And also, now it is time to talk about the research framework, which is the aim of this workshop. You can see the tables, and you saw in the last the tables should be provided in each paper. First, we need to provide climate data, which is necessary for weather data, and the radiance we need for the lighting. The climate data includes direct normal radiations, diffuse horizontal radiations, total sky cover, and the direct normal irradiance. Actual radiance is the amount of solar radiance perceived by a surface that is always held perpendicular to the rays that come in this straight line from the direction of the sun and at its correct position in the sky. And diffuse horizontal radiance, it is actually received by a horizontal surface which has been scattered or diffused by the atmosphere. It is a component of global horizontal radiance which does not come from the beam of the sun. And then when you want to sum up these items, you can receive to this total sky cover as you see in the picture right now. A metric that a metric that looks at a specific light level at a set time and time using localized sky condition to review lighting design and glare is point-in-time simulation. For example, we have an overcast sky and want to calculate daylight for example, hour 8 on the Wednesday in July. So we use DF for daylight analysis. So this is the specific time and date and months for this simulation. After a while, there is some researchers found out that there is a bug with this point-in-time simulation. So when we use point-in-time simulation, because the sky has a dynamic status, right, and the static condition, it has less accuracy rather than the dynamic simulation, which we call annual simulation. And now it's time to start with the honeybee. Work on a honeybee. If you let me, I want to share with you the file also. Now I want to actually start with modeling with honeybee. First of all, we use the construct bereft to separate the construct bereft for divided the box into some faces, and we use list items separated each face. Now, because of we have 6 faces, and now we have 6 list items. Okay, now as you see in the picture, let me turn off the display of it. Now, okay, and then we have this one. This is the wall. This is the wall, the next wall, the next wall, and this is the floor. So you put it in here right now. The wall, and this is the floor, okay? These are the wall, we merge together. Then we use actually honeybee to transfer the grasshopper algorithm to honeybee modeling for ready of simulating honeybee. Yes. Oh my gosh, there's a one. Excuse me, please let me check it right now. HP face. HP face. Yes, we have HP face. And other things. Oh, this is a high plus. Maybe honeybee. Honeybee, yes, there is. Now we have HP face right now for wall. So this is HP face. I want to show you by this bifocal. So the type is wall. We say wall, and we type it and wall, and then match the wire to this. Then we use. Actually, I think this is a floor. The next one is a floor. Yes, it's a floor. Say floor. And what's the problem with it? Yes, because of the geometry. And the lower because of the name we have. Then we use what? Roof. Roof selling. Roof selling. Yes, and then we use honeybee. Yes, we use HP role right now to create a room with the spaces. The conditions is related to the heating and cooling, so we toggle true because we want to analyze for thermal comfort. And then we use HP Salt Agency to be sure that all of things are working well because of the cycle, because of the intersection between each wall. Then we use HP Add Subface because of the window we have, and we use HP Aperture to add this one. So this is a as you see in the picture, this is a window we have. So we put this one, and the name is window. And we toggle the this operable as is because of the we want to aperture can be want that our aperture or our window should be opened for ventilation. So we toggle it for this one. And then we use HB add shade because of our shading we have. HB add shade, and we shade HB shade for others. And actually we have because I want to disconnect this one because of the it's no, I think yeah. Now it's time to flatten tree. Flatten tree. Okay, because the data management, we use flatten tree to match all of the trim surface together. This one for me. Then we use this one. This one. Actually, the shades are the triangular shape you see in the picture. I mean, these shades are modeling it honeybee. And then now excuse me, it's this one. And then we use, actually we use HP model for creating our model. And then now it's time to actually analyze daylight. So we use HP radiance, recipe, and HP annual. Then as you see in the picture, we have model. This is a model, and we have the model, but it is need to add a component that is a role of that has the role of intermediate. So we use HP assign gradient views, and then we put this model to this one. Actually, this component needs grid and views. The view is not necessary, but grid is so important that you add it. I like to use HP radial grid from room, and the room is this one. Put it right here, right now, and the grid is here. Actually, it has error because of the grid size. We have not matched it. Grid size can be number 2. I want to tell you what's this one, and the distance below can be 0.76. Okay, and last time I told you that what is it? As you see, oh my goodness. Please, okay. Oh my God. Please consider this room. Right now it's the box that is created, and then it has a floor right now. So a user actually sit on here right now, and it wants to work with a laptop on a desk. Okay. So it is a window right here right now, and then the grid size is about the floor. We want to separate the floor, divided in 2 meters. For example, 2 meters like now, and this is divided into and 2. This is a 2 meter and 2 meter, 2 meter and 2 meter. So actually, each grid has the area of 4 square meter. So we use grid size and 2. And distance floor is referred to your desk, your work plane you have, and the height of the work plane from the floor. It can be 0.78. So the height of can be 0.76. And then, thank you. And then we need weather for the annual HP annual daylight. So we use, for example, we use HP weather from EPW because we have this output and this input. It should be matched with each other. So then thank you. Then we put this one. And we need type file path, and then attach to this one. We can we'll select one existing building, existing city. I put Tehran right here. And then there's a threshold, and the north has a default 0 degree, and the threshold has a default value. We can put it based on the desired value, but I put in excuse me, I put in T 300, and then about the schedule, you can put it in here or not. It is not necessary it's not necessary. But the schedule means that when a user come to the when a user come to the office, this schedule. Excuse me. This schedule. The user when coming to the office, the schedule is from 8 a.m. to until 4 p.m., for example. So actually, the schedule is that we can put it in here right now. 8 a.m. to 4 p.m. from January to actually November, December, and we can say that from one of the first day of, for example, January, from the last day of December. Okay, this is the schedule. And then, thank you. Thank you. And then it's time to toggle it through for Ron.
We
this
can
is a Ron setting. Could you please turn off your microphone? And then it is time to. Could you please turn off your camera? Excuse me, microphone. And about the radius parameter, I want to tell you about the radius parameter after the about the material. It is so soon right now. So we toggle and through. We turn on toggle and through for the daylight analysis right now. Thank you for your listening. Thank you for your listening. My son, thank you. Okay. Now we have yes, and that is actually for actually if you want to see your results and visualization, you actually use LB spatial daylight, LB spatial then a spatial heat map, actually, excuse me. And then we put the mesh from this one. So I just need to turn off my. Excuse me, what's wrong? Then like this. What is it? Because H radial. We say HV. It's the radial grade. We say we use HV radial grade. This is for grade from now. Yeah. So yeah, as you see in the picture, you can see the actually daylight result from this actually capability of ladybug tools. And then if you want to use SCA, you can use this components, and you can put mesh in each other in this way. And now also you can see the value. So it meets actually the lead, the amount of lead. I want to teach you about the DA, the next step, DA and SDA that you are watching. So it's time to go to the PowerPoint. Now, now it's time to actually go to the word of annual simulation, that it has its metrics, and the type of this guy is dynamic, as you saw in that actually in that slide. We have some actually a variety of sky that is used. It can be used for dynamic or annual simulation, and now it's time to understand about the metrics of daylight. First of all, we have daylight autonomy. Daylight autonomy defined as a percentage of occupied hours of a year when a minimum illuminance threshold is met by sole daylight. As you see in the picture, this is a formula of this metric. It is a local index and long-term and one-tail. Also, there is another metric that related to the daylight, and it is extracted from SCA. SCA is extracted from the DA. For example, if your DA limit, we consider about 300 logs, and your DA, I mean, when you excuse me, when you when your result receive, for example, to I don't know, receive to actually 50% or 55%, you can have you can meet the amount of SCA. The SCA is met the meet the lead criteria, and then because of that. And then if your DA limit would be 300 likes, so your STA get 0. And the definition of the STA is that the percentage of point of analyzed area which meets to exceed the horizontal illuminance threshold of 300 likes for at least 50% of the occupied hours. So it's important that you know about it. For example, the important point is that analyze area. So, and then at least 50% of occupied hours. These are the points that is different from the A. And actually, it show to you the best way of definition of the DA and SCA as is in the picture. DA 300 lux is the fraction of occupant time in which daylighting achieves 300 lux. So this is a fraction of occupant time, and it is based on percent. And then we have SCA is a fraction of space based on percent, and daylighting achieves 300 lux in at least 50% of occupant hours. And the other metrics we have is useful daylight illuminance, and also it is defined as a fraction of time, also as the same of the A in a year, when indoor horizontal daylight illuminance at a given point falls in a given range. Actually, this matrix has a lower and upper limit. Values are proposed in order to split the analyzed period into 3 bands. And this is the formula of EDI, as you see in the picture. And it is also a local, line term, and two-tailed index. I'm gonna tell about the difference of the zonal metric index. And UDI informs not only on useful levels of daylight illuminance, but also on the frequency of occurrence of excessive levels of daylight that might cause occupant discomfort and unwanted solar gains. And now it's time to talk about the features of material. These are some features related to the material that is used for daylight simulation, and one of them is roughness. Roughness, when we say high roughness, it has a matte appearance, whereas the one actually with a low roughness, it has a shiny appearance, and we say specularity. And the specularities can be seen as in the picture for the for both of the sphere in the picture. And in this picture, you can see very well all the features of the material in terms of daylight simulation. You can see the specular because it's so bright and diffuse when this is so fade, and this is the ambient. When we say a specular reflect, when you sum up the specular reflectance and diffuse reflectance, it is equal to total surface reflectance. And specular reflection is when a light faces with the surface, and then with the following angle, it reflects to the space. And the diffuse reflection is when a light faces with a surface, then with a various angle, it reflects to the space. This is another trick that clarifies the definition as is in the picture. This is a specular when the same picture, the same angle that we have, and this is a spread, and this is a diffuse, and we can combine each other. For example, diffuse and a specular, or a specular and a spread, or diffuse and a spread. Another picture that we see in the picture, this is a when a light beam instead actually a phase or deal with the surface and then reflects from the same angle to the space, we say a specular reflection. And then when the light beam reflects the space with various different actually angle, we say diffuse reflection. And this is the feature of a reflected scatter distribution material. Otherwise, when we have then the incident beam, the light beam penetrate to the actually the surface and then gets out from the other side of that. This ray or it is called a specular transmission, and the name of this material can be BTDF or transmitted scatter distribution. And there's another picture that you will see in the slide. Right now, we get into radiance modifiers. I think it's better I told you in the next step. Now, stop sharing. It's time to add the material. Now, before that class, I put it in here right now because this opaque modifier should be searched for the amount of each feature, for example, reflex and specular roughness. These are extracted from a paper I have remembered. And for example, for a wall, we say brick. So the brick has each features. This is a brick. We say to red modifier, and then for opaque modifier, already attached to this one, and then for a shading, yeah. And now it's time to merge. And then the material of the shade is light metal. And this one. Now it's the outer shape. So it's time to, about the window. Forget about this. So for glass, we have transmittance of 0.65 68. Now it's time start with this modifier as is in the picture. you know. And about this one, when we wanted to analyze the daylight, we say we use a radiance parameter and then relate to the modifier material. So it's better we say a radiance parameter, yeah. Radiance parameter. Recipe radiance parameter. So then no. Okay, the recipe can be, as you see in the picture, our matrix is related to the annual, so we say annual, and this is the 2. In detail level, we want to actually render in a low, so we say low, and then as you see in the picture, this is radiance parameters that we provided for your paper as a table. And then it's time we go to the PowerPoint structure. Yeah, actually, as you see in the picture, this is a radius modifier. We have modifier type identifier, and for a glass, we have modifier of the glass, and we have 3 objects, for example, red, green, blue, and this is related to transmissions, and it should be lower than 1. And for glass window, it is 96%, 0.96%. But you can actually customize based on your the type of your visible light windows. You can customize it and you can change the value of it. For example, as you see in the canvas, I use 0.68 for visible light, or for based on visible light, and for the transmission. For the plastic, you can see we have 1, 2, 3, 4, 5. We have 5 feature, and these are RGB is the color, and these are the specular and roughness. For example, for plastic and metal, for plastic we have 1, 1, 1, 0.03, 0.01, and for actually metal, we have RGB specular and roughness, and we have 0.68 for red, and 0.27 for green, and 0.002 for blue. And for specular, we have 0.95, and for roughness, we have 0. Also for mirror, you can see that because of this picture, because it's the material, the type of this material, we have 111 for RGB because of the color we have, and it does not have any specular or roughness. The other thing that you can see in the picture, it is related to the simulation parameters. Ambient bounces is the AB, and is the maximum number of diffuse bounces computed by the indirect calculation. And if you use higher value, it provides better accuracy. And for ambient accuracy, we say AA is the maximum error permitted in the indirect irradiance interpolation. And if you use lower values, it gives you the best accuracy. And ambient resolution actually assess the distance between ambient calculation, but determining the maximum density of ambient values used in the interpolation. And if you use higher values, it provides better accuracy. And respectively, you can actually study about these parameters from the Facade Harvard papers. It is it's so popular in the world of research and academia. So it's time we go to the next one. I'll tell you about the visible transmittance that is in the range from 380 to 700 nanometers. And the larger the number you have, the more visible light will pass through the glass. Visible transmittance, a measurement of the amount of light in the visible portion of the spectrum that passes through the glass. We say visible transmittance 0.5 would be visible transmittance, 50% of the light is getting through. As you see in the picture, you have the incident sunlight and can reflect and is also transmitted. And that's all. It's time to go to the right now. And then yes, as I told you, this is a radiance. You can see this is a plastic and this is a modifier. We see RGB and specular and roughness. It has 5 arguments or 5, we say, what we say? Argument or yes, argument. We say argument. And for glass, as you see in the picture, we have three actually arguments, as you see in the picture. We can use number 1 and then it convert to the mirror if you use it. About the radius parameter, as you see in the picture, based on the table I described for you, this is the AB, and this we have 3. This is the AD, we have 5,000, and this is the AS, we have 128, and etc. You can customize based on your desired things. For example, you can use additional parameters. And the next one is now it's time to go to the view. It's time to go to the view. So now for view is in Ladybug. It's in Ladybug, and I forget about that dimension. What is it? Honeybee. Then as you can see in the picture, we use HP face, HP room, HP sub agency, HP add subface, HP add shade, HP model from the desktop. Okay, and then for visualization, we can use it, for example, visual types by HP visualize by type. And then for analysis of the daylighting, we use HP radiance. Yeah. So respectively, we use basic properties. For example, we use HP assign gradient views, and then we use HP sensor grid from room. So these are extracted from the first tab, and then for modifiers, we use from this tab. As is in the picture, these tabs I mentioned about the material, we use material and this material. And then for light source, we use actually weather data, and then it is not here, it isn't here right now. And then for recipe, we use HP annual daylight, as is in the picture. And the next one is SDA, spatial data autonomy, as is in the picture right now. So it's important that you use the components respectively from the first tab, from the actually left side of you to the right side of this tab, this toolbar, I say. Then we go to the view. So we use LB view%. Now, first time we should provide a view type, should provide the view type. And actually, if you stay in here right now, you can see the type of the various type of the view. We can use, first of all, we can use, for example, The first one is that if you can consider that you have a sphere right now and in 3D model and excuse me, horizontal, I think. Let me share it. Check it. Number one is a horizontal 30-degree offset. Yes, the band bounded on top and bottom by 30-degree offset from the horizontal plane. Okay, you can consider that you have a circle and you have some direction within 30 degree. Excuse me, it is so hard for me with default. Yes. 30 degree, within 30 degree. So we have some direction and we have some direction for the view as in the picture. So this is the type we select for this. Thank you. And we put it in a way number one. The resolution is not important. About the geometry, it is your actually floor. Your floor, we say this floor. What is the floor? Floor is this one. But I think it runs the problem with the side of the floor. So we use a flip. We use a flip. And the context is what? The context is everything. Let me get this all the same. And the context is all of the things that prevents the sunlight to penetrate through your space. For example, we have, oh my God. For example, we have a room and okay, this is a floor and we put as a geometry, okay? And the contents is in the walls and the roof and all of things that you can consider as a prevention of receiving the daylight. So we say the shading on the on the window can be considered. Thank you. And now the shading I use merge. Excuse me, could you please turn off your microphone? Then the shades, okay. And the other thing is that your room is this one. You know, I just before this workshop, I just delete or use the call index or delete the walls as a as a window. This step is related to a window, so I add to this one, and then as a context, I'm thinking right now, flatten. Okay, and then we use grid size. Grid size, as I told you about that, we can consider the number 2. And offset and distance, and also is 76 I think I want to mention about that. There is actually the field of LEED. If you read about the LEED criteria, you can see the amount of 76 centimeter, the height of your work plane or offset distance. Then we can toggle and use toggle and through. Yes, let me turn off or yeah, that's it. That's it. Horizontal 30-degree offset view. This is the result of your view percent, and you can see your result when you put it here right now. You can see grade 0 have 50%, grade 1 have 21, grade 2 have 25, and others. Then the other thing is about the thermal comfort. Now, it's time to I explain about the view. I want to share with you the same PowerPoint. Okay, so as you see in the picture, this is all the type of the views. We say we use the type number 1 views. I think it can be yes. So this is an example of a view rating 1 to 5, and this is actually the definition of view is that is it clear when we say unobstructed things like this one and obstructed things like this one. What's the definition of the lead? Lead from the view of view is direct line of sight to the outdoors via vision glazing for 70% of all regularly occupied floor area. At least 2 of the following 4 kinds of views, multiple lines of sight to vision glazing in different direction at least 90 degrees apart. Views that include at least 2 of the following. You can see the flora, fauna, or sky movement, objects at least 25 feet from the exterior of the glazing. Unobstructed views located within the distance of 3 times the height of the vision glazing. Then head height is the height from the floor to the top of the window. I want to show you. For example, we have window, and this is a user back of the window, and head height is this one from the floor. Yeah. It said that unobstructed views located within a distance of 3 times the head height of the vision glazing. For the next slide. This is the head height. This is the head height. And the user, actually, it's important that you meet the criteria as explained in the last slide. Then now the next one. Yeah, it can be see clearly from this picture. This is a window distance. This is a view direction. This is a horizontal view angle. Vertical view angle, the glazing area, window to wall ratio. These are the actually definitions of view. So, and this is another picture. This is another paper that related to the quality of daylight, quality of view, and daylight energy efficiency from that is written by Peyman Puleciha and Dr. Mohammad Jawad Mahdavi Nejad, and you can refer to it because it's so popular paper in academia. And also, and now it's time we go to the thermal comfort. The other things related to the GA and SGA, related to the Galera, I want to mention is and this cheat sheet for the next session. So we go to the thermal comfort. So admit, okay. And then actually, this part is related to thermal comfort, basic and standards definition. In this lecture, the aim issue related to the thermal comfort will be presented. The percentage of thermal comfort of a person derives from the primary need to keep the temperature of innermost parts of the body in the range 36 to 38 degrees centigrade. To ensure this, it was necessary that the heat produced because of our metabolism and our activities balances the heat delivered into the environment. Comfort sensation drives from the imbalance or balance between the heat produced and the heat lost. So when we are cold, it is a warning that we lose more heat than we produce, and our body is cooling down. When we are hot, we produce more than we lose, and our body is warming up. The human body not only produces heat, but also mechanical work. This is when walking, running, cycling, climbing, and etc. The total energy produced is called the metabolic rate. Thus, the energy balance of our body can be written as M, W is equal to actually is a mechanical work, and Q is heat loss. The metabolic rate is expressed in met or in watt per square meter of body surface area. 1 met is equal to 58.1 watts per square meter. And then a stated percent, as you see in the picture, produces 1 met. The higher is the activity level, the higher is the metabolic rate, as you see in the picture. Yes, this is another picture that describes very well. The human body heat with the environmental convection, which depends on skin temperature, earth temperature, and speed, and relative heat exchange, which depends on the temperature of the skin and the temperature of the surface enclosing the space, and transpiration, which can turn into sweating in the respiration, which results in the evaporation of water with the consequent removal of heat from the skin or lungs. It depends on the relative humidity of the air, and conduction. It takes place if a part of the body is in contact with a solid object. It depends on the solid object. It depends on the temperature of the skin and the object, as well as on the thermophysical characteristics of it. So thus, the heat loss is given by Q, and is equal to C is heat loss or gain by convection, R is heat loss or gain by radiation, E heat loss or gain by evaporation, and H is heat loss or gain by conduction. Of course, the heat exchange between the body surface and the body and the environment depends also on the clothing you wear, as clothing acts as a thermal insulation. Clothing is measured by its thermal resistance, and actually is expressed in the unit 1 kilo is equal to 0.155, and per square meter Kelvin per watt. And the value actually is equal to 1, correspond to the typical winter, as you see in the picture, clothing. And the lowest value is 0 when we have a naked percent. Yes, and summarizing, in conclusion, the body heat balance. The thermal comfort depends on the 6 factors, of which 2 are personal and 4 are actually environmental. The personal is activity and clothing, and the environmental are air temperature, air relative humidity, air relative velocity, and mean radiant temperature. So this is actually the best picture for categorizing of these two types of two category of the environmental parameters and personal parameters. And about the mean radiant temperature, deserves some more words. Consider fire. The thermal effect of a fire on our body does not depend only on how big is the fire, but also on the distance we are from it. And the closer the fire, the higher the heat flow reaching us, and the bigger we see it. If we are far away, we see the fire as a small dot, and its hidden effects on us becomes negligible. Also, with radiant heat, the apparent size of each radiating surface must be taken into account. Not only its temperature, the apparent size is measured with the so-called view factor. I'm gonna show you in this one of the components. A specific index, the mean radiant temperature, was now introduced with this view factor, and then the mean radiant temperature, it defines as the uniform temperature of an imaginary enclosure in which the radiant heat transfer from the human body is equal to the radiant heat transfer and the actual non-uniform enclosure. It is important to note that the mean radiant temperature is function of the position at which it is measured. Actually, this is a particularly critical aspects of thermal comfort to consider in rooms with a large glazed surface, as you see in the picture, and consider a room as the one in the figure, in which 3 walls, we have 3 walls that are opaque and 1 glaze. Suppose that the glazing temperature, because the outside of the temperature of the solar radiation absorbed, and it has a temperature of 38 centigrade, and all the other surface, actually 3 walls is in the picture, are at 26 centigrade. If the person is close to the glaze like this one, in that position, the mean radiant temperature is 29.1 centigrade. If instead the person is in the corner of far from the glaze area, in this position, in the other position, the mean gradient temperature is lower than 26.9. If we are in an air-conditioned environment with 60% relative humidity and negligible air movement, the only environmental parameters affecting our heat balance are air temperature and mean radiant temperature. For this reason, a synthetic comfort index has been introduced. The operative temperature defined as the mean between air and mean radiant temperature. Going back to the previous room, we say if the room is air conditioned and the air temperature is 26 centigrade, the operative temperature in 2 cases is respectively 27.5 and actually 26.5. It is evident that the person close to the glaze area actually feels hotter than the other one if the air temperature is the same. And about the PMV, predicted mean votes, to take into account this effect, the European standard EN 50 to 151 on comfort temperature to be maintained in heated and air-conditioned spaces refers to the operative temperature, not to be air temperature. The PMV model differs from thermal comfort surveys carried out on a large group of people exposed to the same environment. The statement was about their thermal sensation on a 7-point scale from cold to hot, from -3 to +3. From these surveys, empirical equations were derived capable to predict the thermal sensation in terms of predict mean votes. In order to predict the number of people likely to feel uncomfortable in an environment, another index was introduced, the PPD, predicted percentage of dissatisfied, which provides a quantitative prediction of number of thermally dissatisfied people. And yes, this is a suggested comfort zone as you see in the picture in the chart. And in non-air conditioned buildings, the principles of adaptive comfort can be applied. Which takes into not only the purely psychological factors, but also include, physiological and behavior factors we have. The issue of adaptive comfort is addressed in ANSI or ASHRAE standard 55 in 2004. The standard applies the principle of adaptive comfort in spaces without air conditioning. And when the system is turned off and where the thermal condition of the space are regulated. Also, it is designed for sedentary status, for example, for office work. Primarily by the occupants through freely opening and closing windows. And these conditions are actually the value of operative temperature for which the environment is perceived as reasonably comfortable depends on mean monthly outdoor air temperature. Acceptable comfort conditions are met when indoor operative temperature are within the limits indicated in the picture. There are two set of operative temperature limits, one of for 80% accessibility and the one for 90% accessibility. The 80% accessibility limits are for typical applications, and the 90% limits may be used for a higher standard of thermal comfort is desired. The graph tells us that in non-air conditioned spaces, comfort is achieved with temperature higher than the in air conditioned space. And concluding, thermal comfort is the main driver of energy consumption in buildings. The more uncomfortable is the space, the more energy is necessary to make it comfortable. For this reason, the knowledge of thermal comfort principles is crucial for designing energy efficient buildings. And it's time to go to the grasshopper. And we start with actually thermal comfort. So we use HP energy. Now for daylight we use HP radiance, and then for for energy and thermal comfort we use HP energy. Yeah, that's it. So we use thermal. We use thermal PMV comfort map. Am I sure? Am I true? Am I right? Yes, PMV. We say PMV. We have PMV. So first of all, we should actually we simulate about simulate and model with the construction and material materials related to the energy. So first of all, we use HP search construction. And for wall, we want to extract it, the materials. So it recommends us adiabatic wall, a generic exterior wall, generic interior wall, and until 77. So now, for example, we say we want to select one of them, for example, 01. Yeah, 01. And then we use basic properties for HP construction and for exterior construction subset. Yes, this is a exterior wall, so exterior wall, and this is opaque, but the opaque construction is related to the exterior wall. And then we match it to the exterior subset. Actually, the material of the wall is created, and then we use another thing. We use want to create it for floor. So this is actually, it is an opaque material, so it is not necessary to change it. So yes, then we use it as a floor. The other thing is about roof. Type it roof, and then we match it for exterior roof. And now our material for energy is created. Then we match it to the HP room construction. The another thing is that false. The another thing is that related to our window. So we use another thing. We say window, and then match it to this one, and then we match it directly to the aperture. Okay. Then another thing is related to the shade. We have shade. You can see the shade, and then shade construction. Then we put it in right now to the shade. We right now the shade, AP construction shade. Construction, reconstruction, 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 and reconstruction. Yes, that's all. And then it's turned to HP Peony comfort map. It needs model, so we use model of which one? HP assigned grid in views. We should provide EPW. We use actually we can use HP radians, but the output is not related to the EPW. So we use Ladybug tools, for example, Ladybug tools, and from this one, APW downloader. Yeah, you use LB downloader because the output is as the same as the input of this plugin component. And then with this one for better URL, I provided it before that from Tehran. Put it in right now. And for DD file, put it this one. North is default. run period, we can actually use an also tree for this one, but that's necessary for this. Airspeed, you can use it, use some numbers for airspeed or metabolic rate or a clue value. Or comfort parameters, you can use LV, PMV comfort parameters. And also for radius parameter, you can see you can match it to this one, but not necessary. And now, we say we can use HP recipe setting, but it's not necessary because it can save in another default folder. And now it's time to toggling through. And it's like it takes a long time because it is thermal comfort. Guys, can you hear me very well? Because I think I'm in a dark room and I don't have an idea about this. Can you hear me? Good girl and good boys.
Yes, we can hear you.
Thank you, Azada.
Welcome.
Say, now I missed your comments. Now we actually we're gonna finish our workshop because of that. But I'm gonna tell you and show you the results that I before I give from those components. Then I send you uh, uh, the GH file that I have provided for this workshop. It's so clear. But I sent to you some algorithms related to the outcomes of the workshop. Don't be actually worried about this. I'm going to put it off because it takes about 30 minutes. Yes, if you let me, I want to turn off it. And then another thing, another way, this is actually this, the result is can be here right now. A soft share again. You can see the picture. Okay, you cannot see the picture because I'm sure my shirt is limited. Yes, now I think you can see my screen. Yeah, this is the result of DA. Galera, I'm gonna tell you about this one for the next session. This is the result of PMV, you can see, and this is the result of the visibility percent as in the picture, see in the picture. And also you can, you have seen and and during this session. The other way we can simulate for thermal comfort is in here right now. Okay, this algorithm. I provided it right here and now. Actually, output model, we have model power from this one, and EPW power. Now, let's read. Excuse me. I think we're into the problem of the analysis of information. You can stay on the components, read about it, as you can see in the picture. Each actually input describe any criteria, any factors very well. And also you need to study the papers and also search about it more and more until you get the meaning of each factors and parameters. And this is actually because of the limited time we have for the workshop, we cannot cover all the factors and definitions and all aspects of the using components for the daylighting or glare and thermal comfort for today. Yeah, it means to spend a lot of time to understand deeply about this knowledge. Okay, it's not necessary. I sent to you this actually this algorithm. Yeah, and it's time to go to the slides related to the some definitions of the tell me what some comfort factors. And I think that you see the pictures. Yeah, actually. For example, air speed, the rate of air movement at a given point in time, regardless of direction. Flow, I actually told about this one. Metabolic rate, I told about this one. But I have written in this slide for you. Relative humidity, I told about it, but I want to show you the formula, this one. And mean radiant temperature also, and predictive results, predicted mean vote. I told about this, but I have written and put it in here right now. And about the predicted percentage of dissatisfaction, I actually describe it for you. And then local discomfort, the term for unwanted cooling or heating on a particular part of an occupant's body. Main conditions can include draft, abnormally high vertical temperature differences between the hip and ankles, too warm or too cold flowering, or too high of radiant temperature asymmetry. And this is, yes, it's actually related to the thermal comfort. And now, yeah, I think that's end. Can say goodbye for now. Guys, it's finished.